We are predicting states of matter. We're starting out our General Chemistry 2 class with states of matter. So why is this a big deal? Well, it helps you understand a lot of around what's going on around you. How much energy is it going to take to boil a pot of water, or more complicated things like if you end up with you need to trying to think of something that's not a pure compound, but when you're heating up things or cooling them down, it takes energy. So being able to predict that, and it gives you the feeling of controlling it, even though you're just doing a really good job at predicting it. But it really helps you understand the world around you and make really good predictions. So let's talk about these different, we better talk about the phases of matter are first. What are those, Steph? The phases of matter. Ooh, good. Solid, liquid, and gas. Mia, how do you, I was supposed to pick on you first, Mia, I apologize. Mia, how do you picture a solid, a liquid, and a gas? What do you picture the little molecules doing? Like, do you have a mental image of a solid, liquid, and a gas? And I guess if you or anybody, if you don't, you want to get one in your head because it'll really help you. Okay, good. I agree. The liquid's going to be moving. Yeah. Yes, good. I like that. How about gas? Spread out more. In fact, think about it as interacting. That's how I think of it. Because you have a solid that interact. Which one are they interacting the strongest on? Solid, liquid, or gas? Anybody? These solid, right? These molecular interactions got to be the strongest for solid, because that's what they're really stuck together, right? Liquid, not. There has to be some interaction, otherwise it wouldn't be a liquid anymore. Turn into a gas. Okay, so with that picture in your head, Enrique, if we have a plot of energy going up, what would be at the bottom of the energy scale? Solid, liquid, or gas? Liquid? Now, I think this is another concept that will help you in the long run. When they say more and more energy, and you're talking about molecules, so we have these pictures of solid, liquid, gas. You add energy, you're really increasing the what? There's the T. Temperature. That's really what they say when you're increasing the energy. You're increasing the temperature. Okay, well, fine. You increase the temperature. What does that mean? What are they doing differently? These molecules got to be doing something differently. They're moving faster. Now, what could they do? They could be spinning faster. They could be flying through the room faster. They could be vibrating faster. They're just doing things faster if you increase temperature. Okay, that might help you. Which one of these, solid, liquid, gas, anybody, is at the bottom of the energy scale? Solid. Those things aren't moving hardly at all. If they were, they would be a liquid, or moving more, a gas. So at the bottom is solid, liquid, gas. Gas at the top. So what we need to do, Andre, is we need to keep track of energy. So if you're going up the energy scale, what's the convention? Is that positive energy, or is that negative energy? I mean, they're both energy. It's just that they want to put a sign on it to keep track. Oh, you're losing and you're gaining. If you're going up the energy scale, you're gaining energy, so the energy has to be positive, right? So that would be positive energy. You're going up. You're going up, it's positive. If you're going down, then it's got to be negative. You're losing that energy. Okay. We had words for negative or positive energy, heat, negative or positive heat, kilojoules, Bowdy, endothermic, and exothermic. Which one of these was positive energy? You're going up the energy scale. We had the very first Let's see. It was Monday. We blew up that balloon. Yeah, endothermic energy is going in. Just misspelling in is all, right, to N. But yeah, in the very first day we blew up that big balloon. The delta H was negative. We said it was exothermic. So that's giving off all this heat. These water gas molecules, when we combine hydrogen and oxygen, they were just flying out of there, generated so much heat and energy. Okay. So endothermic is positive, going up. Exothermic negative. Okay, phase transitions, converting from solid to liquid, or gas to solid, or liquid to gas. There's a whole bunch of them, Megan. What's a phase transition? Can you name one? Any phase transition. Melting. Melting's a good one. Okay, Audrey. Wait. Yeah, right. You're right. I know. We'll wait on that one. Melting is going to fall under the endothermic or the exothermic category. So look at, melting is going from what state to what state? Solid to a liquid. So then look at the little scale there. It'd be endothermic, right? Does everybody agree? Because you're going up. So we can definitely put, what'd you say, melting? Melting over here. So if I'm going to melt something, ice in my hand's going to feel what? Cold, because the ice is sucking up the heat to convert from solid to liquid. All right. Okay. Connor, another phase transition. Yeah, well, what would you call it, though? Liquid. What's that? Evaporation. Okay, evaporation. Kendall, evaporation is endo or exo? Evaporation. Endo, liquid to gas. Evaporation. Another, Kenneth, phase transition. Condensation. Condensation, Steph, is endo or exo? Condensation. Exothermic. Does everybody agree? Condensation, because condensation is going from gas to liquid. Going down, it's got to be exo. Now, you're on a picnic, especially in San Antonio, Texas, right? You'd think that, yeah, it's your sodas or whatever is getting hot simply because it is hot. That's very true, right? It's just sucking up heat from the environment. But also, you've got a lot of condensation going on. And condensation is huge. That takes a lot. I mean, you know it does. Go swimming. Get out of the swimming pool. You have this evaporation going on. You can get chilled pretty fast. So it takes a lot of energy to convert water from liquid to gas. Okay. Let's just do one more and we'll quit. Mia? I guess I'm back to you already. Weird. Okay. Freezing. So freezing would go where? Endo or exo? Exo, yeah. Freezing is liquid to solid. Okay, that's enough. You get the idea. How much heat? Does that make sense before I go on? Oh. When I say positive or negative, let's back up, Enrique. Let's make sure you're following me. I say like melting. Positive or negative. And it's supposed to be energy. What units do we always use for this energy? Kilojoules. Because we're in the metric system. I'm surprised we're not sticking with calories because we're supposed to be British, but kilojoules or joules. So how much heat is needed to boil 20 grams of water initially at 70 degrees Celsius? We better end up with an answer of what units? Kilojoules or joules. All right, that's what you're looking for. All right. And that's one thing to realize. The other thing to realize is you're pretty much, in these problems, Andrea, you have to put on the plus or minus sign. So if you're starting out with water, you want to boil 20 grams of it. It's at 70 degrees Celsius. And you want to end up boiling it. So we're going to end up, in the end, kilojoules or joules, depending on what they give us, right? But is it going to be a positive or a negative sign that you have to put on? Positive. Does everyone see why? You're going up that energy scale. So those are, we haven't even done the problem yet, and you're already expected to know this. You have to do all that on your own. Okay. So, Bowdy, how are you going to figure this out? Now, you can't figure it out with what's in italics. They have to give you that kind of information. How are you going to do this?
Well, you have to change the grams, right?
Change the grams to moles. Why is that going to be helpful? Does anyone see what she's looking at? Yeah, she's looking at this. And you may not even see the concept. And you see what you got to do. Really. You really don't even need to know the concept. You got to get rid of those moles. So convert those 20 grams into moles. Multiply it so the moles cancel out. I'm in kilojoules. Do the same thing with this guy. Now, this guy also has a Celsius on the bottom, though. So not only do I have to multiply it by moles, I have to multiply it by temperature, right? So whether you understand it or not, the units tell you what to do. But let's get the concept behind it. The total heat, right? If I'm at 70 degrees Celsius, am I a liquid, solid, or gas for water? If I'm at 70 degrees Celsius. Because what temperature does it boil at? That's another thing they're assuming you know. In Celsius, it's 100. And it has to be 1 atmosphere pressure. We'll talk about that later. But it's going to boil at 100. So you have to heat up the water. Heat up 20 grams of water to 100 degrees Celsius. That's going to be so many kilojoules. Then, okay, now it's all at 100 degrees Celsius. Now you have to convert that liquid to a gas. So there's 2 steps. Convert 20 grams of water, liquid, to 20 grams of water, gas. And that's going to be so many kilojoules. Add them up, and we'll have our answer in kilojoules. Does that make sense? Because you can't just go ahead and boil the stuff right away, because water boils at 100. And it takes, notice how it takes different amounts of energy to do this. So that's why they have to give you these 2 things. So if we're going to make this work, this first one, Megan gave you a hint already. Or not Megan, didn't Bowdy or someone did. Anessa. There was a hint. Someone gave a hint. How are you going to figure out this first one? Okay, let's do that. How do you convert grams? We want to convert, let's do it off on the side somewhere here. 20 grams of water into moles of water. Oh, I think I just picked on Bowdy. Audrey, how do you do this again? Well, she stepped out. Let's pick on Kendall. Kendall, you got to help her out.
Wait, what did you say? Convert it
I want to get this into moles, yeah.
Okay, so we do 12 grams of H2O.
Yeah. 12 grams of H2O
Over 1 mole.
over 1 mole. So each hydrogen is 1, oxygen 16, so that should be 18 total. So 20 divided by 18, you get about 1.11. Okay. So we've got the moles. Now what, Connor? And then do what? Yeah, times the 1.11 moles. All right, he's canceled. So he's in kilojoules. Just make sure this guy's in kilojoules. And he will be if we work this out right. So how about the next, Kenneth, how about the next term? How are you going to mess with this? We're going to have to use this one. We're going to have to use that one. Anyone see what to do? Hold on, I'm confused here. Right? Didn't I put this in the wrong spot? Right? Shouldn't the convert 20 grams of water to 20 grams of solid? That should be over here. Right? I screwed up. Right? Because that's converting liquid to solid. That's vaporization. That's where we use this one. So it's okay. That just put it in the wrong place. Right? So that one is that one. This one, now we have to use this. So more heat, more temperature change. See, what do you got to do? Multiply by temperature, then by the moles. Let's do one at a time. 0.075. You know, what's on top and what's on bottom here with these units? Good. That's really important to see. Right? You see how the moles and the Celsius are on the bottom. So I get rid of those moles. We said it was 1.11. So those are gone. And you can only add kilojoules to kilojoules, so we got to keep going. We got to get rid of those degrees Celsius. So how are you going to do that? It has to be the change in the temperature. You can't multiply it by 100 degrees Celsius. Yeah, that's going to give you the wrong answer. Can't multiply by 70 degrees Celsius. That's going to be the wrong answer. You got to multiply by the change in the temperature. All right, which is going to be how many? Well, we can write it in. 100 minus 70. And then you get your answer. Do you want to remember an equation for this? The book's not giving us an equation, so I didn't. Ooh, Q is heat. There's a delta T in there for the change in temperature. Yeah, MS delta T. And that's really not even quite true. It's really probably M, maybe C, because it's really not a specific heat, but anyway. But they're not giving us an equation, so we just have to use the units of what we're given. Then over here, we had to get rid of those moles is all. Convert all that 20 grams of water into gas. Let's see, 0.075 times 1.11 times 30. Add that to 46 times 1.11. I get about 53.6 in the end, kilojoules. And it has to be positive. I put that sign on there. Okay. So there will be some homework like that. Just realize they want to change state, right? You have to get it to that temperature first that it's going to change state at. And that's why we start talking about phase diagrams, because at what temperature is this stuff going to actually change temperature? So that's all what a phase diagram is all about. It's about, hey, pick any pressure and temperature, and you can get the phase, the type of phase. So if it's is this compound a solid, liquid, or gas at this pressure and temperature? Use a phase diagram to get it. So here's a phase diagram of water. This is pressure. And I think you're going to want to, the book's expecting you to know this. How to draw the phase diagram of water. It's kind of nice because almost all phase diagrams are identical. Okay. So what is it going to look like? In general, it's going to look something like this. And then we draw a couple dots. So do you see three regions? Here's a region, here's a region, here's a region. So solid, liquid, gas, they have to go in there. Where would they go? Enrique, where would you predict, where would you throw solid? Region 1, 2, or 3? It's not an easy question. You got it, though. Why 1? Because if something is really, really cold, right, make it really, really cold. So that's going to be way to the left or way to the right? Way to the left. It's going to be really, really cold. So that rules out pretty much rules out 2 and 3. Make it super cold. It's going to turn into a solid. So there's solid. How about liquid and how about gas, Andrea? Where would you put gas? Oh, so your first guess is good because heat something up as high as it can go. You know it's going to be a gas. So crank up the temperature as high as it goes, go as far as you can to the right. That's all region 3. So that means the middle guy must be liquid. Okay. So what good is this? Well, you said, or we said, that water boils, Anessa, at what temperature? 100 degrees Celsius. Well, what's our pressure in this room? We were supposed to say it's 1 atm, 1 atmosphere. So at 1 atmosphere, if we made a plot here, let's just say that's 1 atmosphere, 1 atm. You go across, down. This must be 100 degrees Celsius then. That's how it works. Bless you. Okay. So let's see if we can use this phase diagram to make some predictions here. Well, first let's make sure you're seeing this right. If I crank up the pressure, Bowdy, what happens to, let's back up even more. Where's the boiling point curve? Where would you figure out the boiling points? What part of this phase diagram? Yeah, between 3 and 2. Here's your boiling point curve, right? So as you change the pressure, what temperature are things going to boil at? So they call it the boiling point curve. They call it the vapor pressure curve too. Okay, and we'll talk about that in a little bit. But that's the boiling point curve. If you want to talk about freezing points, what line would you be looking at to know the freezing point of this thing, this substance? Between 1 and 2. All right, here's your freezing point curve. All right. And then, man, can you go from a solid to a gas? Yes, you can. That's how snow disappears at the North Pole. It's called sublimation. Yeah, it's not very common, right? You don't hardly ever hear about it. So sublimation curve, but I wouldn't really worry about it. Okay, how do ice skaters skate on ice? So is ice a smooth surface or a rough surface? It's smooth if you do the Zamboni thing, right? But it's really pretty rough. They look at it under a microscope. It's really pretty rough. And so, I mean, you have metal on something pretty rough like sandpaper. It shouldn't work. You shouldn't be able to skate on sandpaper. So what they're thinking is what? With the ice skating. Because they're just sliding around. They're flying. It's really slick. You can break your neck. That blade is extremely what on the bottom? Sharp. Narrow, right? So the narrower it is, the higher the what as that person stands on it. There's the P. Pressure, right? Think of a fat blade. The pressure isn't going to be near as high because that force, that person's weight is dispersed over that big fat blade. So make it really thin. Then it's going to be really high pressure because it's exerted all in a very small area. Because that's what pressure is, force per unit area. So they're saying, okay, under that blade is a really high pressure. So what happens to the freezing point, or the melting point in this case? What happens to the melting point of water as you crank up the pressure? The melting point goes, right? It goes down, right? Crank up the pressure. That means you got to go this way. So as you're going this way, temperature goes down, right? Because you get these different, here's, at this pressure, there's a freezing point. Crank up the pressure, now the freezing point is here. So you crank up the pressure so high that it's not going to freeze until it's minus 30 degrees Celsius or something. Well, heck, it's not that cold in the ice skating rink. So under that blade, and only under that blade, is going to be liquid ice. Sorry, liquid water. Liquid. Well, liquid is slick as snot. You're going to fly. Okay? So for many, many years, they thought that's how ice skaters skate. But now, I don't know, people do this research on the funkiest things, and now they don't believe that's the case anymore. But so it's exactly how ice skaters skate. It's a good question. But it's a good story. Okay, vapor pressure curve. Vapor pressure curve is this one, right? And where is it? You got that part. What is it good for? Well, you can tell what the what is. The at different pressures. The what point? Boiling point. It's a very hard concept to get. So if you can tell where the boiling point is, why don't they just call it a boiling point curve? They call it the vapor pressure curve. What's the big deal? Okay, see if I can illustrate this to you. What is vapor pressure? Here's a liquid container of water. Vapor pressure. Does liquid water go into, is water evaporating? Is this water evaporating? If I pop it open, jeez, crickets. Ah, there it is. I pop it open. We come back on, what, Friday? This level will have gone down, if not totally disappeared. So is water evaporating? Yes. So water's going from liquid to gas. Cap it. Is water evaporating? No, yes. Is water evaporating? Yeah, it's evaporating, but it's also condensing at the same rate. So it's at equilibrium. Dynamic, remember? So, yeah, so that level is not going to change height. But the point is that you do have water in the gas phase. Well, then that goes back to the picture of a gas. How'd you picture a gas again, Connor? Spread out and doing what? Flying around, right? So how can a gas exert a pressure? How can a gas exert a pressure? Boom, boom. Higher pressure, boom, 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 boom. This is why you shouldn't sit in front. Gas molecules are hitting the surface, right? And the harder they strike, the higher the pressure. So that's how they exert a pressure. So what is vapor pressure? It's just the water molecules up here exerting a pressure. No big deal. So what is vapor pressure then? Which is just water molecules exerting a pressure, right? No big deal. What does that have to do with boiling? Okay, now you got to think about this. I increase the temperature of this. Will I have more molecules in the vapor phase? Most definitely. So if I have more molecules in the vapor phase, the vapor pressure went up. Okay, I'm going to heat this up so high so that the vapor pressure is the exact same as, what do we call this? Atmospheric pressure. I'm going to heat it up so high so that the vapor pressure is the same as the atmospheric pressure. Now it boils. So that's why they call this a vapor pressure curve. Because if you want this thing to boil, the vapor pressure has to be the external pressure. So if you want this to boil, and this curve is always about boiling if you're on that curve. So this is the vapor pressure at this temperature. But it's also the external pressure, because that's where it boils. So vapor pressure finally reaches external pressure. Now, what does that have to do with anything? It does for the people in Colorado. Colorado. They're going to make Asian garlic chicken pasta in Colorado. Why not? Right? Do they have to do anything differently than we do? I don't know. Read the directions. Shit. At high altitudes, do this. They do have to cook differently. Why? There's less pressure. Okay, so if you're going to make this pastaroni, you have to make it in a what? A kettle, right? And you got to boil the water. Well, is their water any different than ours? But what does differently than our water? What does it do differently? No, I mean, their ovens are just as good. I mean, their burners are just as good as ours. There's less what in Colorado? High altitudes. There's less air pressure, right? Now, since there's less pressure, there actually is less oxygen, too. But the point is that the pressure's lower. Well, if the pressure's lower, and when do things boil? When does this thing boil again? When the vapor pressure is the same as the atmospheric pressure, the external pressure. Well, if the atmospheric pressure is lower, you can't heat it up as high. It's going to boil. Their water is going to boil before ours will. Their water probably boils around 95 degrees Celsius. 95 degrees Celsius, ours is 100. Who cares? These guys do. Because they don't want those guys to be cooking for 2 minutes or whatever, and they're eating that pasta that's chewy, because it wasn't cooked at as high of a temperature as we cook ours. So they give special directions for high altitude people. Okay. And those special directions very often involve something we haven't talked about yet, boiling point elevation, but we'll get to that later. Okay. Does that make any sense? Bromine, oh, we didn't talk about the points. Okay, we should talk about the points. Oh, that's okay, we'll answer with this question. Bromine has a triple point at negative 7.3 and 44 millimeters of mercury, and a critical point at 315 and 102. Now, what the heck? They want us, look at this, they want us to sketch a rough phase diagram of bromine. We're missing some information to do that. Let's redo the phase diagram of water. This was pressure. This is temperature. Remember, you're supposed to be able to draw this. And I drew 2 points on there, 2 dots, but I didn't tell you what they were called. So this one, everybody, is the triple point. It's where all 3 phases are there. So at some particular pressure and temperature, you get the triple point of water. So you can go to Mars and calibrate your thermometer by just making the triple point of water, because you know what, that pressure and that temperature has to be the critical point. It has to be the triple point. And then up here is the critical point. So we had solid, we had liquid, we had gas, but notice how that vapor pressure curve, it stops. It stops at the critical point. So once you're beyond this temperature, There's no liquid. No liquid can exist, I should say that. It's too dang hot. And it gets into a whole new state. We said solid liquid gas, but there's actually more. There's how they decaffeinate coffee. Coffee's a big thing. You don't want to mess with people's coffee. If you want to get caffeine out of there, it had better taste pretty much the same. Now, yeah, the taste will be a little bit different because there's no caffeine. But you don't want to mess with all that stuff. So how do you get the caffeine out of that nice coffee bean? Well, you use supercritical fluid carbon dioxide. Supercritical fluid doesn't even exist. There's supposed to be solid liquid gas. No, there's another one, supercritical fluid. There's plasma. There's a lot of different states. So you get supercritical fluid, which is going to be way up here in CO2's phase diagram, and that dissolves caffeines wonderfully. That's how they decaffeinate coffee. So anyway, we're supposed to know those two names of those 2 points. The other thing we're supposed to know is on water, and on water only, really on water only, does this line go back. And that's a big deal. I remember teaching this physical science class, and it's really curious how there's so many very peculiar things, and without these very peculiar things, there's no way life could evolve on this planet. For example, one is that we need a huge-ass moon. Statistically, our moon is way too big for our planet. Mars does not have a huge-ass moon. So what's the problem? Mars' pole is flopping around all the time. Its North Pole is flopping around. If its North Pole is flopping around all the time, its temperature's flopping around all the time. It's not constant. We have a very stable rotational axis because of our huge-ass moon. The location. And there's a lot of things like that. Another one is water. Where does... Okay, let's say you're up in Minnesota, and it's really cold. It's now December, lakes are starting to freeze. Where's the coldest? At the bottom or the top of the lake? The top? You got the sunlight and the little dudes swimming around. At least it's cold, but at the very bottom, there's no sunlight. It should be even colder down there, right? And remember, if you go swimming in the swimming pool, the farther down you go, the colder it gets. Yeah, so the further down you go, the colder it gets. You believe me? Okay, so where will this little ice crystal form first? The bottom or the top of a lake? At the... But where's it coldest? It's coldest at the bottom, so little ice crystal is going to form at the bottom. This little ice crystal goes, does it stay there or does it float to the top? Ice does what in water? Ice floats. So the little ice crystal floats to the top. So the density of ice is less than or larger than the density of liquid water. The density of ice is less than, because it floats. Water is the only compound, well, not the only, but pretty much the only compound known to man, where it's solid, floats, and it's liquid. Everything else sinks. Well, why is that a big deal? Imagine the little ice crystal in Minnesota or wherever sinking. The lake is going to freeze from the bottom up. That thing's going to freeze solid. It has to. Well, where's life supposed to have evolved if you biology majors? It's supposed to have evolved in the water. It ain't going to happen if ice sinks. So that's, and how do I know that any compound with this line going back, when line's going back, that's where the density of the solid is less than the density of the liquid. And that's why they told us this. Density of the solid, density of the liquid. So when the density of the solid, when it's like ice, you draw this line sloping backwards. Make sure it's sloping backwards. Doesn't matter how much, just make sure it's sloping backwards. Every other compound, the density of the solid is going to be bigger. It sinks. Then that line's going the other way. That's why they told you this density idea so you could draw it. So go ahead and draw this phase diagram and put in the numbers, right? See, with the information given, See if you can sketch the phase diagram. They told you the triple point. Told you the critical point. They told you the density. Label the axis labels, the different states. See if you can figure out what it should look like. And then we'll answer the questions. Okay, so what I'm going to do first is I drew my axes, the P and the T for pressure and temperature. You can write pressure and temperature out if you want. And then I'm going to draw the general idea for my phase diagram. I put those in and this. So there it is for water. Do I need to change anything for this substance? I need to change what? Yeah, that line between what two states? Or solid and liquid, right? That can't be going back. It has to be going forward. So that's how I start. That's how I start this. This is my starting point. I just know water, and then everything else I just modify from water. So that's to be going that way. Okay. It says label all the important features. So I guess it's expecting you to label solid, liquid, and gas, right? It's expecting you to label the triple point. I can just write TP, right? The triple point and the critical point. Okay. And if you like drawing little dashed lines to say that's where liquid stops, that's fine. It is really no big deal. Okay. I think that's about all there is really to label. I guess we should put in our temperatures and pressures, though, because look at the question. It says bromine at this pressure and things. So we better write in, give this some idea where we're at. Our triple point is supposed to be at negative 7.3. So that means this is negative 7.3. Yep.
Why was the triple point line going up more towards the right now?
Okay. For me, he's talking about this line. Why is that going towards the right? Because you have to memorize it for water. Memorize it for water. So this is the picture you stick in your brain for water. And then for water, remember, I don't know how you want to remember this. Oh, this is how life evolved on Earth or whatever. But the point is ice floats. And because ice floats, that line's going back, the freezing point line. Because the density of the solid is less than the density of the liquid. And that's always for every compound in the world where the density of the solid is less than the density of the liquid. But it's really rare. So whenever you're asked to draw a phase diagram and it's not water, it's not going to look like that. It's almost always going to be going the other way. Okay, so that's why. And critical point, they said, was, oh, I didn't do the pressure. Where is it? Oh, a triple point, negative 7.3 and 44. So this is supposed to be 44. And the critical point was 315. So this guy is 315. And that pressure's got to be around 102. Okay, so now we can figure out where we're at on this plot here. Let's do purple. Bromine vapor at 40 millimeters of mercury. Okay, so where am I at on the plot? If I'm at 40 millimeters of mercury, I should look at the P or the T axis. The P, because it's millimeters of mercury. So I'm not quite at 44. I'm somewhere below it. Okay. And they said that bromine vapor. So if I want to put my finger where I'm at, where would I put it? Bromine vapor at 40 millimeters of mercury. Put it as a... All right, here? Here's 40. I'm at the right pressure, but I'm in the wrong state, right? Because they said bromine vapor. So I got to be over here somewhere, right? Who knows? I'm somewhere in here. Okay, I'm somewhere in here. So let's put your finger here. Okay, they're saying that it condenses to the what when cooled. So if I want to get colder, I have to go this way or go that way. Go this way. So I'm going to turn into a solid. If I would have been up here, I would have turned into a liquid. But I'm below. They said 40, so I got to start just anywhere in here. And they said vapor, that's why I got to start somewhere in the G area. So you can make it colder, solid. So the answer is solid. See if you can answer the last one. Then we'll call it a day. Bromine vapor at 400 millimeters of mercury condenses to the blank and cooled sufficiently. What's 102? That doesn't make sense. We don't even go that high. Let's change it to 100. Question's weird. I got to change that. 100 makes more sense. It's going to, the answer is liquid. Yeah, you're going to be up here somewhere, and boom, liquid. All right, so we'll have a quiz over this stuff. Try the homework. Come by if you have some questions.